Good afternoon, Putal.
Good afternoon, sir.
Did you manage to download the Coolpack software? It is quite easy. Coolpack software DTU free download. And you can notice this website, ipu.dk, Coolpack. Click this. So this seems to be the website. I just copy this. And I will paste here. Coolpack. Download. And if you go to this website, you can read this, that's all right. You can see download here. So you click here, the download Coolpack version 1.5.0. See, it automatically download. It's a small executable file. You can run it. Okay, that's all. You can run it. I think too early to send the attendance maybe. You can run it. But if you have doubt about power cuts or whatever, I think it's okay. If you need, you can send it. So and also there is another one. See, cool tools. Cool tools. Another one. Yeah. So still under development, this one. So there is the cool tools also. Because for some simple work, you can use this. These are mainly the databases. Coolpack. See, you can run this. Okay. Because I have already installed this, so I'm not going to run this. So you can install this and try to make use of this. This is free software. And for the basic learning of this vapor compression cooling technology, some little analysis, this would be useful. Yeah. So that's all about Coolpack. Okay. And the software I have downloaded here, see Coolpack. At least we can have some database. Would be useful. So free download, so you can keep it handy. Is very useful. So let's go to the daily notes today. I had a little free time, so I have prepared your presentation today. Today, 21st May 2022. So Thermodynamics welcome all semester 2 B2 manufacturing mechatronics and BST for today thermodynamics session. Okay. Continuation from the previous session. I think previous means last week. We missed the session. So before last week. So make sure you download this. So we have learned about the basic, the flashing effect, and the associated the other three components, so all four components connected in a sequence so that there is a possibility of pumping heat from low temperature side to high temperature side. So we have learned this. We have learned this. In our previous sessions. Yes. So this is a simple schematic only. So understanding this is very important. Okay, understanding this is very important. And here you see four components. Okay, four components are here. The four components make this cooling effect possible. Four components. So this all the four components are connected in a sequence, and the working fluid or the refrigerant is passing through one component to the other in a cyclic manner. Okay, in a cyclic manner, so that this working fluid at one place it evaporates. Before that, at one place it flashes and the temperature drops to very low levels, two phase, and then comes to another component there at another place. That two phase fluid evaporates. Then another component, the suction and compression takes place. Suction of this fully evaporated working fluid, suction and compression. Then after that, liquefaction or condensation takes place. Then back to flashing. I think you have learned about the flashing. Same way, you should learn about the compression as well, because actually all the components, what's physically taking place, that is very important. So understanding the systems, quite challenging, but try your best. Sorry, Bhutala. Okay. So try to understand this. So learning refrigeration or the cooling technology is not learning about the components. Okay. Underneath the components, the working fluid passing through each and every component in a sequence makes this cooling possible. Okay. So you have to look little deeper. Then only you can develop the solutions. That's why. So basically from a textbooks, it is very difficult to learn refrigeration, even very difficult to learn about thermal or the steam power plants, okay, or any thermodynamic system. So what's not written in the books, you have to think and imagine and see through the systems and understand. Then only you can make use of this. In short, understanding thermodynamics is totally your responsibility. But we can help. Okay, that's why we have provided you a very good standard text containing all whatever stops within the syllabus. And also in daily notes, we develop the notes together and try to understand something little more meaningful in technological point of view. So you have daily notes and you have one-time note, and also you have these videos, unedited videos, and also you can look into whatever the information in the web or the net and try to understand this, okay? Because it is very important. So we have learned about this. And when it comes to a system, if this functions well, the system should be operated in steady nature. The system should operate steadily. Otherwise, steady means steady in terms of energy and steady in terms of mass when it comes to the operation. So the system operation should be stabilized. Okay. So that is practical and natural. Even our human body as a system functionality, this is well established systems, biological systems in operation. Okay. If that stability deviates due to maybe sicknesses or whatever, accidents or whatever, then it is very challenging for the life. Okay. So same way, even for these systems, there is a natural lifelike thing taking place. Okay. So that should be steadily functioning. It's very important. So when it comes to these steady operations, very important. What nature of steadiness we are expecting in terms of energy and in terms of mass. So in terms of energy, we generally call it energy balances. Any imbalance is energy. It's a problem for the system's operations and the performance. Any imbalances in mass, it's the same. Okay. Natural. That is natural. Okay. So you no need to memorize this. Any system in operation, if it is steady, then only it long lasts. Then only it performs. That is very important. That's why designing a system is not just taking components, connecting and run it. No such thing. Okay. You have to have careful evaluations, component matching. Once all the components are connected, all perform, complementing each other. Okay. And finally, the system perform for our expectation. So that's why learning technology is something challenging, something challenging, and it is more than the textbooks. It is more than the textbooks. Yeah, that is very important. So you should know how to learn technology. That is very important. Okay. Learning technology, understanding technology, and learning technology as the way, the learning of technology. There is a true way of learning technology. You should be looking into those. Otherwise, just for a certification, learning something, sitting for the exam, get the certificate. So that approach is really bad. That's why Sri Lanka is in these terrible situations, because education is not up to the standard, especially the technology education. You see now the current situation. So we have energy issues. Energy related to what? Technology. So we don't have sustainable solution approaches. So finally, those who are involved in technology and engineering, it's the same, and technology is above engineering, of course. So they are not doing their part. Petroleum Corporation, the heart is technology. They failed. Okay. Then the Ceylon Electricity Board, it's a technology. The sustainable solution approaches, it's not working well. Even water supplies, technologies. Even in health sector, most of the cases, from pharmaceutical products manufacturing to the testing and instrumentation, all technology. So we can see in Sri Lanka, even manufacturing, technology. Okay. Even the fourth generation or the fourth industrial revolution being taken place, but Sri Lanka is behind. So technologically, Sri Lanka is failing. And that's the reason we have no local manufacturing, no product developments, no modernization, even in agriculture. So we just become a consuming nation. The issue is this, okay? So we have to learn something very useful way. So you should find the way to learn it, okay? It is very important, yeah. Something useful, realistic, and should be something useful beyond the certifications. Imagine even yourself working in your jobs. I don't think anyone, most of you are technologically, your contribution may not be that satisfactory. That's why long way to go, long way to learn. There should be the better ways to learn technologies, and you should explore those. Okay. No shortcuts. No shortcuts. Yeah. That is very important. Okay. We have the syllabuses, true, but the syllabuses finally should support, complement, contribute for the true realization of productivities in manufacturing, services, agriculture, and all the sectors. In that sense, thermodynamics is a very important subject. If you miss thermodynamics, you will miss a lot of technological contributions that the countries needed. Okay, so if you cannot contribute, you will lose the opportunities. You will have less prospects. That's why. So I'm trying my best to guide you, but learning is totally with you. Okay, Bhutala? Good. So that's why we should learn naturally, and any system should be steadily operate. Yeah, that is very important. But normally when you learn, you may do the energy balances, mass balances, whatever, but you should know that in upfront that the balance should be there for steady operations. Okay, good. So this is the same system here I put. So system means you no need to memorize these things. The system means even if you see this one, you can see components. I just put which are appropriately connected. Here I put in a sequential manner for this simple system. So when you operate the system, of course, for smooth, consistent, reliable, and durable functioning. So steady nature is very important. So operating the system in steady nature. Energy flows, there should be a steady nature. And mass flow, there should be steady nature. Okay. That is very important. Okay. Steady in the sense somewhat stabilized. Okay. You can clearly see the 4 components here. You have learned this. So all the 4 should have steady operations, but all are connected to each other. And you can see because of this connectivity, functionality of one component affects the functionality of the other. So there should be a good match. Example, functionality of the compressor function or compressor depends on the evaporator function as well as the condenser function. Both. Functionality of the condenser, compressor, and this flashing device. Flashing device functionally depends on the condenser and the evaporator. And the evaporator function depends on the flashing device and the compressor. So this component matching in the systems are very, very important. And you are B2 students and you have a lot of practical and technical exposures. And you are working with diploma. You all have diplomas, diploma holders. So you should look into the practical aspects in whatever you are learning. Okay, good. So steady flow operations of a system. Yes, steadiness of the mass flows, as well as steadiness of the energy flows important. But we will look into the mass flows first. So mass flow steady nature. So steady nature means within any component, okay, or within any process, this working fluid undergoing. So within the components, or we can call it as a control volume. Later I will explain. There should not be continuous accumulation of mass for working fluid. So which means whatever in should be out for steady operations. So here, if compression, mass in, at the same time, there should be the similar mass out. That's why M in is equal to M out for any component. So here, evaporate, when mass in M in, the M out also should be equal amount of mass. So even for condenser, M in is M out. So when M in for the flashing device, there should be equal amount of mass out here. So no chance for mass buildups inside. That is what we call the stability or the stabilized functionality of components. And we call it steady flow or somewhat like steady state. Okay, I think instead of steady state, let's say steady flow nature in components. Very important, okay? So try to understand this. So M in, M out. But for this system, example, compressor M out or the mass out or the refrigerant out is the condenser refrigerant in. So this M in, M out should be same. So this M out, M in should be same as the M in, M out here. So M in, M out same, M out, M in same, M in, M out same, M out, M in same. And finally, you can notice that for the system. Okay. When mass M pass through condenser, similar mass M pass through the flashing device. The same mass M pass through the evaporator, same quantity pass through the compression. So this matter of mass M is different from the matter mass M, but all simultaneously at the same time, okay, flowing of the same mass M through the components takes place. Same quantity of mass, of course. Here mass is different from here, but same quantity is passed. So you can see this working fluid is flowing in steady nature. You understand? These are not in the books. These are not well explained in the books. So these are experience-based explanations. So I believe you can agree on this. That's why for system means you can see connected components, integration of components. So for system, whatever the component levels, M in equals M out for any component here. So M in equals M out equals M. Okay. I think you can understand this. So same M. And in the evaluations for the design steady state operations, you may be designing for that, but starting this and shut down or the on-off situations, there can be unsteady nature, but finally this comes to steady nature. Okay, good. So through any component, M in is M out equals M. The same thing I wrote here for this system. Mass flow through evaporator, M in equals M out for evaporator. Mass flow through condenser, M in equals M out for compression. Okay, compression, this one. Mass flow through compression. Mass flow through condenser, a similar mass balance. So expansion of flashing device, a similar mass balance. So when you have this and one component's out is another component's M in. So finally, for the system, M in equals M out equals M for the system. You can see here. For any components, M in is M out. So finally, it's a unique figure when it comes to steady state operations. So this M in and M out, maybe for a period of time, let's say kilogram per hour in 1 hour time. So this is based on time maybe, or even kilogram per second. So can be something like that for a certain duration. But per time means it can be considered as a rate as well. Rate means mass flow rate. Okay, good. So mass flow can be considered as a rate or even a value. So for the system, M in equals M out equals M. That's why evaporator I put in out equals M. Compression, M in, M out is M. Condense, M in is M out equals M. The same M for steady nature. Okay. For the steady operations. So mass flow circulation through steady system. So through evaporator, through compressor, through condenser, through flashing is same as through the system, and let's say it is a common figure, let's say M. And the units of M can be, if it has a flow rate, can be kilogram per second. Okay, good. So nothing complex, no complexities, but naturally, I hope you can understand this. Now comes to the energy balance. It is different from mass balance. So this component has single inlet and single outlet. So single outlet becomes a single inlet for the other component. The single outlet there, single inlet. So no leaks of mass or refrigerant, no leaks. Okay. So no additional mass inputs, no intermediate flow input. So whatever single inlet and outlet, in should be out. But when it comes to energy, okay, if you think of this, okay, condensing example, you can have heat interactions. Okay, I will take the compression maybe. So you can have heat interactions because inside the compressor, sometimes the motor is also there. Or sometimes the refrigerant is, compressor is hot and there can be heat release. So somehow heat interaction with the surrounding. Also there can be work inputs and energy in with the fluid and energy out with the fluid. Same. Heat interactions, you can imagine. Work interactions, imagine, can be zero, but we can put it. Energy in with the fluid, energy out with the fluid. So whatever, so when we take this condenser example, so you can see energy in to the condenser with the working fluid, E in. plus the heat Q in plus the work W in. Okay, should be E out. So E in plus Q in plus W in is E out. Hope you can understand this. So for each and every component. So later there will be further explanations. So energy flow steady nature. Same like in mass flow steady nature. No mass or no matter build up within these processes or components. Same way when it comes to energy. No energy build up. So energy in during this compression or condensation or evaporation. Energy in with the flow. Heat in during the process of condensation or whatever. And work in all together. The energy received by the working fluid during the process should be leaving with the working fluid. So no energy accumulations. So whatever energy level, let it be. So any energy receiving should leave. Okay. For the system or for the components, that should be the way. Because otherwise, if energy buildup means it is not steady. Okay. And this is for the steady nature of operations. Then energy flow through evaporator. Energy in with the fluid. Net heat in. I just put heat in, net heat. And net work in. Later we will see whether these are zero or whatever the value. All together should leave with the fluid, E out. It's the same for evaporator, this balance. Same for the compression. Same for the condensers. Same for the flashing. Okay. So it's the same. So that's how this energy levels remain stabilized. Okay. And this energy flow circulations, finally, you can say that for the system, if the system is receiving heat and work, then the system releasing also heat and work. The sum of heat and work of energy receiving should be same as the sum of heat and work of energy out from the systems. Okay. System is, let's say, the integration or the component integration of components connected in a proper manner to function or to perform a certain function. Okay. So here it is pumping heat from low temperature to high temperature. We'll see that afterward. So energy flow circulation through steady system. Okay. You are familiar with this slide. So when you take the system, evaporator, You are receiving heat because this is low temperature. You are receiving work to the system, and all should be released as heat, because work and heat, all the two forms of energy, but all energy released as heat here. Okay, so your cooling or refrigeration effect is this heat received at the low temperature. That's the refrigeration effect. And your performance is heat received at low temperature, that is pumped out, against this system work input that is provided to the compressor. So compressor is really the component makes this flow of working fluid through the system possible. Okay, so work done on the compressor is actually the work done on this working fluid. So QL by WC is the real performance. So we call this the coefficient of performance, not the efficiency, because even this value can be more than 1. Okay, so it's different, but it is something like efficiency, but this is how the performance is measured in cooling systems. Okay, I hope you can understand this. Yeah. This component can be evaporated, compression, whatever. Okay, so here single input, single output. So for steady flow, you can say flow rating mass in is mass out. Okay, so it's denoted by m dot. And this one is a space. Space is a volume. Okay, so we are considering the space, the heat and work inputs and energy in and out with the flows. And we can write the energy balance. Okay, we can write the energy balance. Good. So here, there should be energy interaction with the surrounding. Also, there could be work interactions as well with the surrounding. Sorry. Work interactions with the surrounding. So energy in with the mass in. energy out with the mass out. Okay. Now, let's say this can be evaporator, condenser, compressor, flashing device, whatever. So here, the inside working fluid. So this energy in plus W in plus Q in. Level of energy being received. Okay. Let's say it's W in, Q in, E out, E in. Okay. Good. Then you can write the energy balance. Energy flow through the component of the system, of a system. Energy flow through a component of a system. Let's say evaporate. Okay. So understanding of evaporator, you have to look into the previous lecture sessions. So energy in. So here Q in net. So I just put Q in here. Plus W in, that's the net value. Equals energy out. Evaporate. If the condenser, if this is a condenser, it's the same, or compression. Again, a component. This way. Yeah, but anything. Okay, you can expect this nature of energy balances. Okay. If it's another component, again the same way. Okay, this is more general. So here there is a keyword control volume because evaporator has a fixed space inside. Through the fixed space, the working fluid is flowing. So fixed space is a fixed volume. So fixed volume is a control volume, is fixed. So somehow controlled, and you have in and out. Okay, so you can understand. I hope you can understand this. Okay, steady flow. So process energy balance. Okay, energy balance. So this is actually energy balance, or we call this steady flow energy balance or equation. Steady flow energy equation or steady flow energy balance. Okay, I hope you can understand this. Yes. Now, this is your daily notes. Sorry, one-time note. I already passed this to you. We will look into. So you have to read this. You have to read really and understanding this. Now, you need to pay attention to this. The topic number 3. Okay. Steady flow processes. So here in our discussions, you can see a steady flow process taking place. Okay. Within all these processes, so when the working fluid passing through the components, so this flow is steady. So you know steady flow. Okay. So it's a constant mass flow pass through all. Notice a constant, the same mass flow in the system. Okay. So back to the notes. You should go through this. See, I got this from your note. Okay, so you can go through this. See, this is about the mass balance, mass conservation. Okay, mass conservation. And here, energy conservations here. But for steady flow energy, there is a balance, steady flow energy equations. See, steady flow process, whatever in, E in to this system is E out. Then for unit mass, the big E becomes small e. Small a is always for 1 kg. Okay, so E is written in this way. So later we will understand this. And you have to go through this. Okay. So no excuses because you are diploma holders and the note is given. So this is considered reasonably good one. So you should understand this. If there are difficulties in understanding, look for any reference. Okay. That is very important. So you look into this. Because our learning has always the connectivity with the notes as well. Okay, good. You have to read your notes. Okay, very important. Then you have a better understanding. So we are connecting these steady flow processes with our application. Okay. So here, energy in for any component level. At any component level, energy in. With the fluid, energy entering the component plus energy received by means of heat transfer plus energy received by means of work transfer. The total energy receiving by fluid at this component should leave out with the fluid because same mass flow in, same mass flow out. So with the out mass flow, E out should be same as the E in plus Q in plus W. Very interesting. For 1 kg, small e, small q, small w, consider for 1 kg means specific values. Put it here. Okay, good. Think about this. So we have to understand this E in and E out. We have to understand what E in means in detail. What's E out in detail. This is very important. Okay, understanding. E in and E out. See whether this will be helpful or not. So I will go back to your notes. E. And this tells that the various forms of energy which the fluid can have are as follows. Means E has various forms or various components. That's why E is H plus Ke plus P. It's mentioned here. Okay. Various forms. So we have to understand this. Understanding. H plus Ke plus Pe. See, this from the note. So E in and E out, or E, consists of various forms of energy. Okay. Contained in mass or relate to mass. Say for 1 kg small e. This Ke means kinetic energy. You have heard about this. This Pe means potential energy, but this is gravitational potential energy, Pe. And here it's mentioned as H. Never mind, H is the enthalpy, you know. But other than kinetic and potential, there is internal energy U plus flow or displacement energy PV. So E is Ke, kinetic energy, potential energy, internal energy plus the flow or displacement energy. So U plus PV is here, U plus PV is H. So Ke plus Pe plus H, or H plus Ke plus Pe is E. Okay. If you are satisfied with this level of understanding, I think it is not very good, because this won't help you to understand unless you know all with the first principles. So you see how this E is Ke plus Pe plus H. So how this is possible? So you should understand that. So E, and this is rewritten as this: H plus C squared by 2 plus GZ. Fine. But you have to understand this. Because if you don't understand, you cannot realize anything out of this knowledge. So H, K is C squared by 2 plus P is GZ. And remember, this is for 1 kg. But 1 kg flow. Because if no flow, you cannot have kinetic energies. Okay, also you have no flow work. So for 1 kg, the specific values. So this E is the energy contained in this flow of working fluid at any point within the system. You can write this. Okay. Entering into a component, example, evaporator compression. Leaving the component, example, condenser or the flashing device, whatever. So entering and leaving. And even some cases, within the components, the flow passage, intermediate levels or intermittent levels, also we can write maybe. So very important, you have to refer your note. Okay. And I'm not doing the note here because if I need to do the note here, then I should stop sharing the sessions because you have the notes and you have the capacity to understand the notes. And actually, I no need to spend time on drilling the knot. You can do it. Okay, so that's why I leave it to you. And of course, no excuses. Okay, you are diploma holders and you know how to learn well. So I presume that it is very important. E in and E out understanding the flow work. I prepared this note little in advance. So let's say this is a pipe. Even evaporator, condenser also can be considered as the flow through pipe. See, flow through a pipe. Condenser flow through a pipe. Even flashing flow through a pipe, but that pipe has a flow restriction. Okay. Compression. Again, if you take pipe as a space or control volume, then compression also can be considered as a flow through a space, a control volume. But that control volume would be variable. Okay. There is somehow a flow passage. Okay, clearly defined flow passages are there. And this flow through this passage, this flow, I consider this flow as a series of elements or parcels, flow parcels. See, one flow behind the other. So moving this way. So one flow behind the other. One flow behind the other. So this series of flow parcels or packets, fluid packets, flowing in a series. Then how this flow makes possible? One packet, push the other, then this moves here, because this pushed this. So the pushing effect, let's say, not the pulling, anyway, net effect is there. So you can see this. This element or this parts push this, and this replace this. Means there is a force and a displacement. Okay. Force times displacement. So you can see everywhere this force times displacement means work. So this pushing effect, force and displacement of the flow. So that's why we call this flow work. So we can actually formulate that flow work for 1 kilogram of flow, unit mass flow, is pressure times specific volume. Pressure times specific volume, PV. So I just type this. So this is upstream, this is downstream. So fluid flow stream can be considered as flow of fluid packets or parcels flowing in a sequence. And there is a flow pushing effect. Pushing means there is a force and the moving or displacement. So that is flow work of one parcel over the parcel next to it at the downstream. So even at inlet, this flow parcel of 1 kg being pushed in, forced in. So force times displacement, flow work is there in the flow into this passage. This can be an evaporator, condenser, compressor, or even the flashing device. So there is a flow work. Work is an energy, you know. Energy received by this flow entering here. So flow work out, energy because of the flow work received by leaving fluid here. Okay. Flow work. So flow work is P times V, pressure times specific volume. I think you know specific volume means per kg. The volume equivalent is specific volume, 1 kg volume, maybe meter cube per kg. And the pressure, P times V, pressure times specific volume. At inlet here is the flow work in. Outlet here is the flow work out. Okay. And you have to think about this because these are physically taking place, and this is the way we can model or we can imagine this with our good sense of understanding of these flow processes. Understand? Good. Back to your note. Back to your note. Give me a second. In your note, where is the note? Yeah, okay. You read this. See, flow work or flow or displacement energy. Okay. So you can try to understand flow or displacement work. Okay, in and out. So you should go through this. Okay, and try to understand. Also with the help of daily note. Yeah. So in E in and E out, understanding E. So we realize only the flow work. See, flow or displacement energy. That is one part of, or one component or one form of the energy within this flowing fluid. In and E out, understanding flow work plus internal energy. So here you can see at this point, there is a flow work, PV, and internal energy is the energy, the molecular level kinetic energy remains within this parcel. Let's say this is 1 kg. So that internal energy plus the flow work, okay, is the flow work plus internal energy at this point. Okay, good. O of this parcel. So flow work PV, internal energy U. So in this E, or within this E, the internal energy and flow work combining U plus PV. You know the definition of H, enthalpy, we have learned as U plus PV. So you can see this H has a great meaning when it comes to thermodynamics, especially for the flowing fluids or for the working fluid. So again, for this control volume, you have to read your notes. This can be evaporator space or condenser space or compressor space or flashing device. Space is a volume. So this can be the control volume. In this control volume, entering flow, yes, contains the internal energy plus. When it's entering, this fluid receives this flow work as well to push this flow into the space. Same time, push out here as well. So very important. Flow work plus U in, internal energy plus flow work in, internal energy plus flow work out. H is U plus PV. So in means H in, H out. So in this E, you should understand what H means. This is for 1 kg. So I will try to explain this way, but you should try your best to understand. So imagine in this parcels, fluid packets flowing in a sequence. So the same mass parcel here, of course, there is a velocity for this. When there is a flow means the displacement is taken place against time. So there is a rate of displacement. We call it velocity, rate of change of displacement. C. So when this mass has a velocity, the associated energy because of this moving mass with the speed, you know, that is the moving mass, the kinetic energy, is half mc squared, half times mass times velocity squared. So velocity we put here C, not V, because V we are using for volume. We know A levels, your O levels, half mv squared may be kinetic energy, but here we will take this as half mc squared because we already have V for volume or specific volume. So for mkg is this, when m is 1, for 1 kg kinetic energy is half c squared or c squared by 2. Kinetic energy c squared by 2, half c squared in c squared by 2 out, because it's a flow in, flow out. Associated kinetic energy c squared by 2 at in, c squared by 2 at out, because in and out may have different velocities. Okay, so it's not the same, but mass flow rates are the same when the flow is steady. Now, this energy due to velocity is kinetic energy c squared by 2. C squared by 2 is here, Ke. kinetic energy. Okay. What is this GZ, potential energy? I put a coconut tree here. On the ground level. Above the ground level is Z, the mass M of a coconut. The potential energy becomes mgz. If this is hmgh, but h we are using for enthalpy, so Z is the height above this datum. So mgz is the potential energy. So imagine this like a coconut, this flowing one. And this level high, if you imagine datum here for the gravitational potential, Z in, so mg is Z in, when this height is Z out, mg is Z out. Okay. When m is 1, this will be g is Z. Okay. Out. G is Z out. Okay. Potential energy means PE. Okay. Potential energy PE. Good. GZ in, GZ out. Or PE in, PE out. CPE is GZ for 1 kg. So now you know this E in much clearer way as H plus C squared by 2 plus GZ, but here H. Two components there, internal energy plus flow or displacement work, PV. So that's how H is U plus PV. Interesting. All the three components are here. Flow plus internal energy is here in this E, U plus PV, that is H. Kinetic energy is here. Potential energy is here. I think I will add that. Seems a better explanation. Okay, good. You read this. For 1 kg flow, E is kinetic energy, potential energy, internal energy, flow work, components. U plus PV, we consider H. So kinetic energy, potential energy, and H, or enthalpy. H, kinetic energy C squared by 2, potential energy G Z. So U plus PV plus C squared 2 plus G Z. I think well explained. Back to your notes. Potential energy is here. Kinetic energy is here. Just a once line of words. But we have explained it very well. Potential energy, we have explained better. Internal energy, you go through this. Flow work is here. So you have 1 potential energy, 2 kinetic energy, 3 internal energy, 4 flow work. So this all together, these 4 components, you can see here 1, 2, 3, 4, and U plus PV, 2 combined as H. So you have 1, 2, 3, 4. Internal energy, flow work, kinetic energy, potential energy for 1 kg flow. I think well understood. In and out. If E is H plus C squared by 2 plus G Z. In, you have the in values. Out, you have the out values. So H as U plus PV, again in, again out. Okay. And flow in, and this is the energy in with the flow. Flow out, energy out. But some components you have net heating and net working. Some cases may be 0 W, some cases may be only W, or some may be both, depends on the process or the component functionality or the working fluid, the process undergoing when working fluid passing through this component. So E in plus Q in net plus W in net. Net means when work in and work out. So say 10 And 5, 10 minus 5, 5 is here, something like that. The network in. All must leave E out. So you have heat and work as well. So energy interactions, you have internal energy, flow work, kinetic energy, potential energy, heat and work. You go here, potential energy, kinetic energy. Internal energy, flow energy, heat received or rejected, that's IQ net. External work done, that is W. So these 6 components, you must have a very good sense of understanding beyond the memory of this. Okay. The same. I put E in detail and E out in detail. Unit. This is for 1 kg. So per kg. Small letters or specific values. This is for 1 kg. Obviously. Okay. One kg. I hope you can understand this. For 1 kg flow. For 1 kg flow. That's our unit, kilojoule per kilogram. But if there is a flow rate, rate means I put m dot, kilogram per second. So for m dot, this is for 1 kg. For m dot rate, m dot times this, plus m dot times this, m dot times this, m dot times this. But for steady flow, m dot in is m dot out, m dot for steady flow. Yeah. Then here, we can rewrite this. So this is the total Q interaction. So we use big Q. Total work interaction. And here m dot times the specific values. Out also specific values times m dot. The system interaction here, you can have big Q and big W. Okay. So if I need to draw this again, this is your system. The energy interactions. So it's not for 1 kg, it's for this component. And m dot flow in. M dot flow out. Good. So this would be the final slide of what good. So this would be the final slide of this SFAE. Let's go back to your note now. It's the same. It's the same. So with the help of your daily notes and your one-time note, you can understand this. Good. Okay. All understood. So this could be any component. Any means that there should be flow in and flow out. So if we go for your notes again, boilers and condensers. Nozzles and diffusers. Because there is flow in and flow out. So two components here. Nozzles and diffusers. If I take the nozzle, you can replace it. Okay. It's the same. So this is your Z out. That's it. Okay. In and out, you can say. If you need to put the diffuser there for analysis, you can replace nozzle with the diffuser. You can do the analysis. Okay. Very interesting. So for diffusers, so you can customize this for the diffusers. You can go through the nodes. Back to the node. Steady flow, these components, even in refrigeration, we have all the 4 components. Turbines and compressors, throttlings in the capillaries and all. You can put here capillary. I will put the capillary here. Flowing. Okay. Flow out. So this is a capillary. Yeah, good. capillary. Okay, good. Go back to your note. You have to understand all, you have to refer all turbines. See? You can put the turbine. In and out. This is not the full turbine, but this says this is a turbine. Okay. Compressor would be an opposite one. Turbine. In and out. The best is for turbine. Turbine has an expansion. Okay. Expansion. Turbine. In. Out. In. And there is a work done. Flow in, flow out. Same parameters. E out, m dot. And definitely there is heat out. But we can have Q net in. Work done. So I just put as W. Anyway, W net in. It's a negative value. Even heat release, but anyway, it's okay. So you can have the similar expression. Later we can customize. So compression. Give me 1 minute. Compression. The compression. The volume decrease compression. You can denote this way. in, out. Nice. Like this. Okay. And later we can analyze. So even though we are learning about cooling systems, today, out of the knowledge of this, we have done this steady flow operation, the energy and mass balances for the system. So later I will email you this. And keep in mind, you have many tasks to do, especially understand by going through the one-time note, so you can understand somewhat. Even though limited, you try to learn this, and also you go through today note as well. I will email you this. So if you are summarizing this in 1 minute, remember to install CoolPack for future usages. I hope you have some understanding. Steady operations we are talking. We discuss what system means. Then steady flow operations of systems. Mass balance, M in, M out equals M. So we have done this very nicely. And energy flows, steady energy flow, or steady flow energy equations, energy balance with the working fluid for any component. And then for all the 4 components, we wrote it for the system balances. And now we came to a note, connect note with this knowledge. So we wrote the expressions, we understand the E, the components or the types of energy related to these mass flows. Very useful knowledge, this one. One-time learning, no repetitive learnings of this. Even you should be able to explain this. If I ask you, how do you, if I ask you explain the flow work in steady flow systems, you should be able to explain what flow work means. Okay. If H is U plus PV in steady flows, what PV means, you should know that is the flow work. So little in-depth understanding is very important. You know all this very well. Later we will do some analysis and we will look into some practical aspects. Good. That's all today. So hope today's discussion will help you. So I will save this as a PDF and I will email to you right now. That's all, Buddha. Any questions? Any questions? This is your PDF, you will be receiving this. So connect this with your one-time note and see how you can gain something extra. So thank you for joining the session today. See you next week, the same time, Putala. I think next week, 28. Yeah, should be okay. See you next week at the same time. So take care, all of you. So that's all. Yeah. So let me email you this. Okay, Bhuta. Bye then. Bye. Since you have listened. Okay, Bhutana.
Thank you, sir.
Yes, sir.
Thank you, sir.
Thank you.